Hello there. Welcome to our next video on the game audio tech tips. So I did a tweet 2 or 3 weeks ago now asking if people would be interested in a tutorial of a reverb prediction blueprint I made, and it went down pretty well, so I thought I would take the time to do it. So what I'm going to do is, let me just quickly show you what's going on. So the debugging is showing from the player character. So you probably wouldn't normally put it there unless your listener's there, of course. I've put it there because it's easier to see the player character than it is the camera. So for the sake of the video, it's a lot, you can understand a lot better what I'm talking about. Another little caveat is, I initially made this a long time ago, actually, in Unreal 4.23. And I've recently remade it, cleaned it up, made it presentable in Unreal 5.2. But somewhere during that process, upgrading wise, the effects just don't work. So I'm going to show quickly Unreal 5 and how I've made it. And then we'll do an actual demo of it in my old Unreal project, which has the authoring built in with the effects that do work. And then we'll come back to this again. So what you can see is in the debugging, then on the top left, we have some numbers. So what this is there's 6 directions that are from an origin point. So we have an origin point and we're rotating a vector essentially. And we're getting some kind of value. And in this case, it's going to drive an RTPC, and then we can do whatever we want with that. To give some kind of comparable measurement, if that's even the right term is. So the number I'm getting here is like between 900 and just over 1,000. And if you drag in like a Wise, an AK spatial volume and show the numbers there. So their area calculation, I don't know how they do it, but it's 1,000. They're reporting 1,000 for this room, and then the hallway over here is at 504, which we can hit. So we're at 530 then, 330, 350. So we're kind of somewhere in the ballpark of how AK do their calculations. I'm not like I said, I'm not sure how they do it, because like if you get the Unreal tool and you draw the room, it's completely different to this one. So it might not even be relevant, but I just thought it was quite interesting to see that it kind of aligned up. So yeah, as I said then, I'll go back to the old project because you would actually hear it working there. And FYI, we won't show the blueprint too much because this is what it used to look like, which is bonkers. So yeah, let's not show that again. And I'll click play. And what we can see now, I'll just full screen. So we have our debugging in the top left with some value, and it's saying that we're in a large room, which is cool. I will quickly just go outside because I want to show the reflections off as well. So as I run along this wall, you can hear the reflections on the wall, and then if I turn around, they go on the left side now. So this doesn't just do late reverberation, it's going to do early reflections as well. And then if I just turn the voice on,
I'm all right. Still a little lightheaded, but well enough to fight.
You can hear it like slapping back off the wall
Don't
there,
worry.
which is really cool.
Through this, promise. Yeah, I agree. We don't want to get hunkered down for too long.
Cool. So let's go back in there.
Did you see them run? Man, we showed them.
And we'll hear it working a little bit better.
Yeah, we sure did.
So this is what we're going to build.
I'm all right. Still a little lightheaded, but well enough to fight. Did you see them run? Man, we showed them.
So things from a small room, and then
Did you see them run? Man, we showed them.
so in the hallway there's a really short
I agree. We don't want to get hunkered down for too long.
reverberation time with some slap back on the walls.
Anyway, don't worry. We'll get through this. Promise. Yeah, we sure did.
Yeah, I think it works great.
Did you see see that run? Man, we showed them. Did you see them run? Man, we showed them.
So
anyway, don't worry. We'll get through this. I promise.
In my opinion, like, this wouldn't replace an actual, like, you wouldn't just use this for your reverb in the game, in my opinion. I don't think you can beat like authored reverbs for the rooms. Like, you're not going to beat that. So this kind of works in addition to that. So for example, let's say you offered a reverb for this room, it sounds great, and then the environment come in here and they start chopping up the walls, adding holes in there, or adding objects in here. You know, the reverb then might need to be adjusted. So in this way, with the other blueprint working alongside an authored reverb, is it makes it way more dynamic. So it doesn't matter if they're going to like section off walls or add in like you know, blow out the walls or anything like that. Like the reverb blueprint will pick that up, and as an additional layer with the authored reverb for the space, they just sound really good together. And I think that's the power of it. That's the idea of it. So let's go through the blueprint then. So last week I recorded this video and I built it from scratch again live, and I kind of spoke about my thought process and I made it more of a learning experience. So I spoke about like the function and anything that like data tables, and I built them all from scratch again, but that just took too long. That was like a 3-hour video. So I think I'll show the blueprint off, and I'll just do like a tour of it rather than a tutorial of building it. I think that's the best way to do it, because otherwise it's just going to be way too long. Okay, so it looks like I had some stuff off the screen. So when I was in full screen there, the debugging was wrong. You didn't quite see the outdoor values or the large room, the medium room, but that's fine because we're going to go over that anyway. So yeah, let's do the tour then and speak about how I built this this blueprint. So what we'll do first is we'll go over the structure because it uses a data table. So the structure then has a direction and then an X, Y, and Z min and max value. So the reason for it being made this way is if, for example, if we were firing traces from here and it hit the character and we only ever hit that point, and then now we move to the right, and then back here, like those values are going to be like dramatic. So by tracing in a cone area, we're more than likely going to get a better result from an average like direction. So it just gives a much better value at the end. And then of course the data table itself has some entries in here. So you'll notice that the row name is just integers, so they correlate to the loops that we're going to go through in the blueprint. So 0 is up, 1 is down, 2 forward, 3 rear, 4 left, 5 right. So it's kind of structured around this. So bear that in mind as to why those are labeled like that. So with the init function then, we're first going to check is it on, which actually I'll just show you on the player. There's some like public variables here. So yeah, of course we can turn it on or off. We can give it an update rate. So mine runs at 0.2. I did some metrics on this, and using Unreal Insights, this runs at 0.03 ms. So pretty good for a reverb for an audio feature at 0.2 seconds. If you speed it up to like a frame, obviously yeah, it looks pretty wild, but actually it's still 0.04 ms. So yeah, but I just feel like the results kind of are it's a bit too jumpy. So I think slowing it down a little bit is better. Not necessarily for performance, but for more of a result in the end. Resolution is essentially what it's doing is it's firing, in this case, 5 traces in each direction. It gets that trace 5 times and then makes an average out of the 5. So if the resolution is 10, we trace 10 times in all directions and then gets the average of the 10 in each direction. So bearing in mind that the more times we trace in a direction, that resolution pool builds up. So to get you your result, it takes longer. So just bear in mind that. And then we have a max distance. For me, it's 10,000. So if our trace doesn't hit anything and it gets to 10,000, we just say that it's the max. And then level of quality is 3 in this case. So if I put that to 1, we can trace. You can see now it's only tracing up and down. And if we put this to 2, it's going to trace up, down, and then forward and backwards. It's not doing left and right. And then if we put it to 3, it's also going to do left and right as well. So it's just like a performance thing. You can just limit your loops. And then the area map is essentially kind of whatever the reverb value is, I'm associating that with some kind of value. This is purely for debugging, really. Like you can have your own kind of database of whatever you want, but for me, just for the debugging purposes, this is basically my like key for it. So we'll go back into the init function then. So we check if we're if it's enabled or not on begin play. It doesn't have to be begin play. It could be something else like when your character changes or anything like that. Next, I'm getting the owner. So it's a component. It's an active component. So I'm just getting my owner. And in this case, my character has some tags on him, and I'm just getting the AK components that have a specific tag. So it doesn't have to be like this. This is just a quick way for me to put it somewhere. For example, if it was on a gun, like you can get the owner of the gun and then get like a joint or a socket or anything like that. It doesn't have to be this. It's just how I did it for this video. Then we set our update rate, and then we enable tick. So it's tick is off by default, because if we're not enabled, then we don't want a tick. Next up, we select our traces based off of our level of quality. So if our level of quality is 1, we're going to do up and down. So we're going to give our reverb traces a value of 1, and because it starts at 0, that's up and down in relation to our data table. So up and down. Next up, we populate our weighting power. So when we get our distance, it essentially uses a weighting power to kind of do something with those distance values. So if we have 6 directions from our reverb trace, that's a value of that's an integer of 5, but including 0, so we have to add on a 1. So basically, if I just click play and I'll show you this, our weighting power is it's just dividing them all by 0.16 to make them all equal to 1. That's essentially what this is doing. I'll explain that again later on. So next up then, we have our actual function, which is Reverb Trace. So essentially we have some inputs here, and on tick, we're going to run this function. So we're just passing in some vectors essentially. So yeah, we get our world location. So like I said, it has to start somewhere. So the traces start at the active location, and then we end somewhere. So like I said, we're rotating vectors. That's actually what we're doing here, essentially. So if I go into the function then, and you can see this is a lot cleaner than the last one that I've shown from the 4.23 days. Obviously, I've improved a lot since that amount of time. And obviously, this is a presentation I'm showing the internet, so like I have to be clean with it, essentially. So it's probably worth saying that this might require some kind of like technical chops. It's built quite well, so bear with me. I'm happy to ask any questions of why I did things again. But yeah, like I said, don't comment on you should have done it this way. Like we're not going to get into that. So essentially, we've established our reverb traces from our init, and we are going to then loop over some stuff. So we get our index value, and then we're going to set a variable called trace index, which is then going to do our directions for us. So we get our trace index then, and we break out these X and Y values. So what I'll do, just for demonstration purposes, I'm just going to put our level of quality to 0, which I think will just give me up. So you can see just the up now is, you can see there's a range of directions there. So if I just literally just break these and then press play, we're only up now because we're only getting the up vector, and obviously the character's breathing and the components attached to the character, so it's shifting a little bit. And then if I just hook them back up, then now we can see, actually let's just do the X and I'll show you this. So if I put 0.5, in fact, I'll just put 0.5 on the X there. You can see now we're not just up, we're offset. So we're pushing this in the forwards axis. Then if I do 1, we can see now that we're pretty much, we're actually kind of 45 degrees from the up. So that's what this structure is doing. It's kind of rotating the values which are populated in the data asset, in the data table, sorry. So this table up is -1 to 1. So this is what rotates gives it the random like range essentially. And then we're multiplying our line trace by the max distance. I'm not doing trace complex in this, but you can if you want. Next up, we break from this line trace and we get some stuff. So we determine our impact point, which is, well, in this case, it's just for debugging. So wherever we impact point, you see I've got these spheres that draw where it hits. So that's purely just for debugging. If you don't care about debugging, you can turn that off. You don't even need to build that in, probably. I'm also getting distance, which is again, you don't need that because we actually do something else after that. So like this runs at 0.03 ms with this stuff in there. You can actually make it better without that. I am doing size to fit purely because it was just quicker to do that. What would be better is if on your init function, you just like you got your level of quality and you added some stuff to these arrays without sizing to fit each time. So you can kind of load your array size in the init and then not size to fit, which is just a little bit better. But like I said, just for the sake of this video being quicker, because I just wanted to show it off. We then got our weighting power. So remember, it kind of weighs it all to 1. And then obviously we need to get that value. So in our top distance, 0.16. So we get our distance value, and then we multiply it by 0.16, and then we add it into this array called weighted distance. So our top like value was 106 in this trace. If I show again, now it's 96. So you can see every time I come out of here and mouse over, this is the kind of value that I'm watching. And it does that for each direction. So like I say, we go through the loop, and then we're getting up, down, forward, back, left, right. So we add them all into it. So the next step then, we have a debug here. So this show debug is essentially drawing our lines for us, doing the trace at the spheres. Actually, no, you do need the impact point. I said you don't. You do, because that determines the line trace, the drawing. And then we also are just getting the distance from adding it onto the text, the debug string there. And then what we do after we have all of these averages, so for example, at our trace index 5, let's say this is the last one, we get the element out of each of here, and then we add them into an array, which is how our resolution works. So if we don't hit anything though, so if this line trace, if we return no hit, then it actually just gets the max distance. So for example, if our distance weighting power gave a result of 20,000, we won't select the true, we would select the false, which is our max distance. So that just kind of stops everything from getting out of hand. And like I say, yeah, we're adding them into an array here. And we're selecting from the index. So we trace the top, the down, the forward, the rear, the left, and the right. We add them all into the arrays at that index, and we just keep adding and adding and adding until we hit our resolution point, which is 5. So for example, if I go here, is it going to show me? No. You can see that this will only ever hit like 5, and then whenever our resolution is hit, we then run another function called set reverb, which we'll look at now. And you can see this working here. So what we do is we populate these arrays by the amount of resolution that we have. So in this case, it can't go above 5 because we clear them at the end. So if I would just mouse over here a few times, you can see that we've got 3 there, we've got 3 there again, 2, 1, 0, 5. So it can't go above there. So we're adding them into each direction, and then we're setting the array element to another array using a reverb average array. So this is a pure function that I made. So what this does is we're passing in an array. So in this case, let's think about the top one. We input the top into here, and then we're setting a variable at 0, which kind of acts as a reset, and then we are getting an average of the array. So for example, what I mean by that is we get a value in, so let's say it's 100 on trace 0. We then get trace 1 in, and that's say 101. Then we add those together, which will give us 201. Then another one comes at 99, so that will now be 300. So we're adding them together in the loop body, and then when it's complete, we pass that value back out again. Yeah, we kind of give it a single float value out, and then we put that into another array called reverb average all. So what this will do, if I just mouse over this one, this is the array of averages for all the directions. So you can see top, down, forward, backwards, left, and right. So this is given as kind of our value in the end. And then what we do is we get the average of each distance. So we get all of these, and then I've got another pure function, which is similar to the average function. So remember, this one gets the average of them all. However, what we're doing this time is we're getting the average of all the directions. So we get the average, we average the averages, and now we're adding them all together to give us our total float value, which is a local variable in this function. And yeah, that's pretty much it. So as long as our total array value is not greater than our max distance, because remember, we don't ever want that, then we select whichever one is better for us, and then we set our reverb value there. So in this case, for mouse over, it's 795, 761, 760. So this is kind of our value for our reverb, and then we're setting this RTPC value. So this happens at the end of a loop. So during the loop then, we've got our averages of each direction. And then what we do with that is we break out of this data table row. So for example, 0 is our top. So we get our average, and then we break out of that. We get the direction, because obviously our data table has our direction built into it. And then just we're appending our RTPC value to it. So essentially we get our value, and then we use the append to set our RTPC. So in this case, it'll be reverb underscore top underscore RTPC. And that's how we can do our like early reflection reverbs, because we have a value for each direction, which is a different RTPC. And of course, we clear out those, we clear them out. So basically, like I said, our average array top, we add in there until the resolution is met. Then we get the average and then do some stuff and then clear that array again, because we don't, otherwise that array will just build and build and build. If I just don't clear it, just to show you, now click play, we can see we're at 7, 13, 17, 21, like that will just climb forever now. So that is what the clear does for us. It just basically just, we meet our resolution, then we wipe that data out, and then count again, then we wipe it out. Yeah, and then we have another debug here, which is our reverb value. So this just shows us, this is showing us now the debug text in the top left. So this is where we use our key map to determine some visual, like this number, you don't need to have a map for it. It's just something that I thought was cool to add. So I'll just quickly talk about that then. For each trace, we check if we can do some stuff, and then we have an array full of distance debug values. And then what we do is we're going to get our area map, and then we're going to see if it meets some stuff, some criteria. So yeah, so what we're doing here then, so when this array is completed, we are going to get it and get our key, and we're going to find that distance value, the reverb value within that. So for example, let's just press play. This is saying that we're in a small room, because our reverb value is, we're finding that and we're checking is it less, and then when it's found it, we do our print string, and actually we need to make sure that there's each loop with a break, because if we don't break the loop, you can see the debugging now, it goes through that loop cycle, and then it doesn't, well, yeah, it's not breaking once it's found it. So once we found that value, we kind of go through the pecking order, and then once we have it, we break it. So that's what the break does. Because obviously, yeah, once we found it, yeah, which is important because you have to build the data table in this way, because that's how it goes through the cycles. Sorry, no, yeah, the map has to be built in this way, because we go from our shortest to a thing. And yeah, that's pretty much it. So obviously, as a tour, you can pause the video and go through this, if you want to do that. If you even want to use it, maybe you don't want to use it, but like I said, I did initially build it from scratch, and I went through everything like in so much detail as like a learning like experience for the viewers, but it was just too long. Like this is already going to be too long. I'll be shocked if anyone actually watches it all, but yeah, that's kind of my thought process. If anyone has any questions, I'm happy to talk about it. Just bear in mind, like I said, like this is how I did it. This is my thought process. So yeah. Yeah, and if you do use it in your own like systems, do let me know, like show me, because it'll be really cool. I'd love to see it in someone else's project. It'll be pretty cool. Just a like disclaimer as well, like this is not in any of my professional work. This is just something that I've done in my own time. Like I'm always making just little stuff as a learning. Like I'm always trying to better myself, and yeah, I'm just like, I think it would work very well in a full production game. I have no doubt about that. Um, it's just it isn't something I've done in my own professional work. So yeah, cool. Thank you.